Alrighty, so we've got that going. Yeah, so and what I'll do is I'll post these to the cloud too, so that, or I'll post them on Canvas so you guys can access that as well. All right, so all logistics taken care of. I gotta say, with all this Zoom synchronous and async or synchronous, like in person and remote at the same time, it takes a little bit to get a handle on all of it. So I appreciate you guys being patient. I also, for those of you that are in person, I would like to be like joking around more and talking more in the moments before, but I'm just trying to get all of this lined up, and it takes so much more effort than a normal class where I would just show up and start talking. But yeah, good to see all of you. So let's see. Let's go ahead and get started with the material. So you guys saw probably from my message that I wanted you to start by coming up with a couple of applications of periodic signals. So you should have generated a couple of examples. So let's start there. I'm gonna spotlight here my piece of paper, and these were a couple of examples that we had mentioned last time. So a couple examples of periodic signals. We got set a sinusoidal and AC voltage. Now, hopefully after some thought, you came up with some other things, either from nature or from engineering systems that could be periodic or repetitive in nature. So how about we start here with just a couple examples. So if you're remote, you can type some examples into the chat. Otherwise, if you are here, you can blurt out some suggestions.
One example I said was like a heartbeat. You can see on a heart monitor, it's like boop, 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 that kind of stuff.
Absolutely, that's a great example from biology. So heartbeat. All right, so yeah, talking about that, you mentioned, so there's on the one hand, it's periodic in nature and the body itself, but you said you could see it in a monitor. And so if you look at an EKG, or if there's so heartbeat, I'll add an EKG, I'll add a pacemaker to that. So if you're trying to make it as steady as possible, that would all be periodic in nature. And notice that these are going to be natural. These are going to be more, say, forced by an engineering system. But and then here with an EKG, you're tracking the heartbeat. So yeah, that would absolutely be periodic signals. Let's see what else I got. Got a bunch of things coming in via the chat. Wow, love it. So let's write some of these down. So from Nick Raff, I have a metronome and fly fishing rod. So I'll write metronome first. So metronome from music, that's a great example. Something that's keeping the beat every second, every however many milliseconds or whatever. It's giving you a knock to make sure that you stay on time. So yeah, that's a great one. Nick Raff, unmute yourself and tell me why a fly fishing rod.
So with a fly fishing rod, the way you cast it is you pull out the line from the reel by hand, and then with your other hand, you go back and forth, each time letting out more and more line until you reach where you want to, the distance where you want to throw the line out, and then you sling it all forward and just kind of, and then to retrieve it back in.
Okay, so
but the main action I'm getting at is like the back and forth of the rod itself.
That's great. So yeah, so you got some nice back and forth motion at steady intervals that's going to allow you to do this and to cast the line the way that you want. Great. Yeah. So see, I learned something about fly fishing today. I had no idea, but yeah, that's a great example. And again, that's going to be a mechanical system that is moving in a periodic fashion. That's great. So what else? We've got a crosswalk there from crosswalk signal from Andrew. Andrew, do you want to tell us a little bit about that, why you chose that one?
I mean, when you have the crosswalk signal, it's just a constant flashing of like the man like you can walk or like the hand you can, and sometimes they'll have the audio too for those who can't hear or for those who can't see or something with the constant like noise of the beep or the saying walk. So it's just a constant repetition of the same thing.
Great, yeah, and certainly in cases where you're on a timer, that's going to keep cycling through over and over, keep cycling through over and over. Now, notice that periodicity would be broken if there's an actual pedestrian that presses a button, right? Like if you go in, press a button, that's going to be, that's no longer going to be periodic in nature. But yeah, if you're on a timer or the beeps themselves, that's absolutely true. And I see Amy mentioned traffic light as well. So this is a similar concept, right? Where if it's on a timer and it's cycling through every so often, every so many periods, or every so many seconds, it's going to change. That would absolutely be periodic. By contrast, if it's a sensor-based one, the periodicity stops. So yeah, that's great. So I'll add traffic signal to that. I'm going to scroll up a little bit. What else do I see there? Time on a clock from Grace. Yeah, and Grace, do you want to tell us a little bit more about that one?
I mean, to me, so like you can either think of it as 12 or 24 hours, but like it repeats every day. You always have like 1 o'clock in the morning, 2 o'clock in the morning, and then like it goes on and on and on. It repeats every day.
Excellent, excellent. Yeah, absolutely true. And whether you're physically, you could be looking at a clock and it's spinning, even the minute hand, it's spinning round and round every 60 minutes, or the hour hand is, and the minute hand is rather. But yeah, same idea. So it's going to be that those situations that repeat over and over. Let's get like one or two more contributions from the outside as we're wrapping up here. So Hunter, tell me about why you chose the sound wave there. Hunter Reiner.
For the sound wave, it's just a sinus wave, like a sinusoidal wave.
Mm-hmm.
So like different frequencies have different different frequencies in sound have different heights of sinusoidal waves. So a sinusoidal wave is just a repeating pattern.
Absolutely, absolutely. And the purest tone in sound, if you get a pure sine wave, it's going to be the purest tone that you can get. If you are, let's say, if you're playing even the same note with a different instrument, the waveform might look different. But if you're getting just, let's say, a pure A note or a pure B note or whatever it might be, it is going to repeat over and over, just with a slightly different shape. And so that would also be periodic in nature. Great. I have Tim there with a guitar effect.
Yeah, so this one, at least specifically like the tremolo, rather than just being like a single note or like a single like pulse that's like just held and let ring out, the like tremolo effect repeats the sound like over and over rapidly.
Yeah, that's a great example. So you keep going back to that, the repeating over and over rapidly. This is great. So I have a few more that I'll just write down here, but I wanna move forward. So if you contributed something via chat, thank you. So turn signal, that's great. What else do I have here? The moon cycle. And I've got this from Thomas, emergency position indicating radio beacon. Emergency beacons for people lost at sea. They made a periodic signal specific frequency. That's great. Yeah. So I'll just abbreviate it as emergency beacon. But that is an excellent application. Alrighty. So those are great suggestions. And here, I mean, I guess I kind of gave priority to those of you that were remote via chat. Ryan Fisher, I saw you also typed into the chat the moon cycle. So thank you for that. Do you want to tell us just a quick bit about it? And
I know exceptionally little about the moon cycle, except that it's a cycle. It's like 2 weeks it repeats. Yeah, you get a full moon every 2 weeks or something like that.
I think it's 4 weeks, but
cool.
yeah,
Sure.
but yeah. So you're going to go through that process of the waxing and waning and so on, and yeah, absolutely right. So any others here from the class before we move on? That was a nice array. Jorge, did you have one? Yep.
The circadian rhythm.
Circadian rhythm, great.
Your hormone levels bounce in different depending on the day to either, make you tired, keep you awake.
So those day-to-day rhythms about, whether it's about sleep, whether it's about, there's a lot of rhythms in the body, right, that are going to be based on that 24-hour cycle. Absolutely. So in the body, we had earlier the heartbeat suggestion, but then you've got these others that might be, so think about like, sleeping and waking. That's great. Anything else that's different from, let's say, from here in the class, different than has been mentioned? Okay, so I'll throw one more out there, or one or two. So how about, I guess it's related, but like day and night in nature, and also the seasons. So this might also not be 100% periodic in that the length of the day and night changes a little bit depending on the time of year, but for the most part, well, certainly if you're in the equator, it's going to be fully periodic in nature, and same for the duration of the seasons. There's that cyclical nature to it. So I think it's good to look at all those examples. So you see that both in engineering systems and then in natural systems, periodicity shows up all the time. So we're going to be doing quite a bit in this class with periodic signals. And I think if we don't go through this example, you're like, why? Are there so many things? Are there so many things that for which it makes sense to think of it in terms of repetition? Now, for all of these, I think you can see if things repeat every so often, the first question you can ask yourself is like, what is that period? So how often do they repeat? And if you're asking yourself that, you can also ask yourself frequency. So how many cycles per second do you have? And a lot of the things we're going to be doing are going to be based on frequency. So so this is a good thing to touch into. So anytime the periodic signals come up, you can think to all this range of applications. And I think it's worthwhile. Otherwise, like this class, it's easy to just get lost in the equations and feel, oh, we're doing a lot of math, but why? So again, we are going to be able to model all these different things. Now, mathematically, the main characteristic here with periodic signals is that we can write it, a signal is going to be periodic if x of t is going to be equal to x of t plus, let's say, capital T, or let's call it t sub 0. Okay. And I'll say this is true for all t. So this upside down A symbol, that means for all. Okay. And then this T0 right there, that's going to be your period. So that's the main definition. Now, remember what having this T plus something meant in the parentheses. Do you guys remember from the last class? It's going to be the time shift, right? So if you've got like this situation right here where you got T plus T0 right in the parentheses, it means you're taking your signal and shifting it. And so what this is saying is that if you check the signal at any given time, it's going to be the exact same thing as it is if you check it shifted by a certain amount, in this case, that period. So it doesn't matter here if like t is equal to 0 or t is equal to 20, it's going to be the same that it was one shift over. And then obviously if you shift it by the next period, it's going to be the same over and over and over. Now, let me ask you, would it be the exact same thing? Can I say this? Minus. Could it also be true? I see a lot of nodding right here of saying, yeah, this also works. And Andrew via the chat agrees with me and agrees with y'all as well in the class that this also works. So this is saying, yeah, if I shift in the other direction, that's still going to be the same. So yeah, so this is going to be the main characteristic to these periodic signals. We've already worked a little bit with them when we did the power. So we know that with power, we can integrate over one period. We don't have to do necessarily integration from -infinity to infinity. We can look at one period because we know that repeats over and over. Great. All right, so that's one type of classification of signals right here. So the periodic versus non-periodic, which, by the way, yeah, I guess I should have zoomed out and backtracked a little bit, but yeah, we're just looking at the idea of classifications of signals, and in different ways we can group them mathematically. So we had looked at different types of applications like electrical signals, mechanical signals, etc. We also want to see mathematically what are different types as well. So that periodic versus non-periodic is a pretty typical classification. Here's another one that's a pretty important one: causal versus non-causal signals. So I'll give you here, causal signals have this particular characteristic. Basically, x of t is going to be equal to 0 for all t less than 0. Okay, so an example of a causal signal would be something like this. Let's say we've got x of t versus t. Basically, it just means that before time equals 0, before I start counting, it's got to be completely flat, and then it can do whatever. So that would be a causal signal right there. Now, if I have a signal like this one, let's say I've got x of t, and then maybe here on the right side, maybe I have, whatever. Even if I've got like some small blips here on the left, this would be considered non-causal. Okay. Also, if you've got, I'll do another one right here. If you've got a signal like, oh man, I missed that. I missed someone sneezing and then everybody so politely in that E-Town way saying bless you. Don't hear that. Don't hear that on Zoom. So that's nice. Let's see. So x of t versus t. And so another one that, for example, in circuits, sometimes you're coming in and you're looking at a circuit that is already charged, like it's pre-charged. And then afterwards, it uncharges like that. That would be considered a non-causal signal right there. So this one right here would be causal. These guys would be non, because for it to be causal, everything that's on the left-hand side, everything prior to t equals 0 needs to be off. It needs to be like powered off. Now, in a lot of examples that we're going to do in this class, we're going to work with just causal signals and causal systems. And I'll talk about a causal system in the future. But these are, Ryan, can I ask you to close the door? Thank you. Yeah, I guess that's different about in-person classes too. It's like you do get a little bit of noise. Like at home, it's just, my cat might meow every now and then, but it's not nearly as much. I kind of miss hearing Scanlon's cackles though. Like that hasn't happened this semester. Yeah, maybe in a few weeks. Anyway, so back to it right here. So in general, we're going to be working with causal signals, which are going to be ones that were essentially, think of them as being off prior to t equals 0. T equals 0 is a little bit arbitrary. It's basically just when you start counting, like when the system starts being important for you. Again, something like this one on the right side, it might be non-causal, but you might think, wait, does it have physical significance? It does. Again, you can think of something that basically before you started looking, before you started counting, already had a certain energy associated with it already was charging, for example, in the case of a circuit. So that's causal and non-causal. And at any point, feel free to interrupt me if you're here, or otherwise you can type into the chat if you have a question. But that's another good say classification of signals. That's pretty important. Here's another pair that is going to be pretty damn useful to us to understand. So it's all based on time for this one. Continuous time versus discrete time. Continuous time signal versus discrete time. Excuse me. All right. So pretty much everything I've shown you so far, all the examples that we've done are continuous time signals. And what that means is that on my horizontal, when I look at time right here in my horizontal, that this is going to be essentially just one continuous line, even if it's got jumps, but basically for any value of t right here, I'm going to have a value of x of t. So if you, yeah, like let's say we've got a causal one right here. Let's say it started at 0. If we've got, yeah, any sort of, whatever it does, doesn't really matter. But as long as right here in my horizontal, I don't have any skipping around, I don't have any values of t for which the signal does not exist, we would say, well, that's going to be a continuous time signal. All right. By contrast, and you're like, well, what else, what else could exist? A discrete time signal, put it here on the right. So to make the difference between the two, I'm going to put, instead of calling it t, I'm going to call it n right here. And I'm going to call it x of n with a bracket for discrete time. So one on the left is continuous time. And this one right here is going to be discrete time. So the main difference is it's not true that in the horizontal, every single value is going to have a corresponding value of x of n. It's going to be, essentially, you're just checking it could be every second, it could be every millisecond, or whatever. And so we're going to create essentially a little grid on my horizontal, and we're going to give each of those points a corresponding value. So for example, here I'll do, let's say that I'm starting here at 0, and maybe I am gradually going up right there, something like that. And so maybe that's going up, and then maybe you're, oh, it looks like that COVID curve a little too much. So let's say we're we're coming back down here. So something like that would be an example of a discrete time signal. And so this would be the case if you're only checking at certain, giving a number for every certain intervals right here. So it's not atypical. You might see even like a little dashed line showing you where you are corresponding to each one. Oops. Something like that. So that would be a discrete time signal. Now, discrete time signals come in all sorts of different, so let's look at some examples here for each. So examples of like applications of discrete time. I mentioned the COVID case as being an example of something that could show up like this. And it's true. If in the horizontal, you are looking at, for example, days, and maybe this is, maybe this is day 1, this is day 2, this is day 3, this is day 4, this is day 5. It's not true that there's a day between day 4 and day 5. There's only so many days. And so time itself, there's no way that you would naturally think of as being in between. Or same if these guys are years right here between, let's say instead we could have, I'm going to draw another one. Like let's say I have something like student population, or yeah, let's say student population versus time. Maybe you're looking at 2009 and you had so many students. Maybe you had 1,700 students in 2009. And maybe in 2010 you had, 1745. And maybe in 2011 you had even more students. You had like, I don't know, like 1820 or whatever. So over here, if n in this case is years, it doesn't make sense to think of a year between 2009 and 2010. There's just nothing in between, right? So by its very nature, the time is going to be discrete. Same here, you might be thinking of n in days, and that might also be the case there. Now, it doesn't always have to be that big. You can be thinking of n being like milliseconds or nanoseconds if you're working with, let's say, with digital applications, with computers, things like that. So anything where you're only counting from like one beat, essentially one beat to the next, and only taking values there would be discrete in nature. So yeah, so things like this, examples, so things that are like population studies would be an example of something that's discrete. What else? Financial. So financial studies of kind of financial signals. So if you are tracking, for example, a certain investment month to month, then it doesn't make sense to think, okay, between March and April, what happened? You just be looking, March, something happened, April, something happened, whatever. So that might also be discrete time. And then anything based on a digital clock, let's say a computerized clock. So computerized systems. So in my horizontal axis with computers, you're really only checking what happened at a certain interval, then at the next one, then at the next one, then at the next one, and it's not going to be this continuous line. So that's something important there. Examples of continuous time signals, though, is going to be just about, I'll say almost, but almost anything in nature. So things kind of, just by their very nature, if you're tracking velocity of an object versus time, you're position versus time, or voltage versus time, the nature of most things in time is going to be continuous. A sound wave by itself is going to be, continuous time. So just about anything is going to be, or I'll say, yeah, really like in nature or any physical system. Physical systems, that's going to be continuous time. So notice there are going to be, yeah, some specific applications here for discrete time, but almost everything is going to be continuous time. The thing that becomes a little bit tricky is that, so those of you that are right here in person, you are definitely getting continuous time in terms of my voice, or in terms of like what your eyes are perceiving when you see me and when you see each other. This is all continuous time information. Those of you that are at home and are perceiving all of this stuff via Zoom, you're actually being fed a discrete time signal via the computer. And so it's pretty interesting. You're still eventually hearing something that's that your ears are picking up, and that might be made into something that's continuous. But for the computer to be able to process it, all of this here that was initially continuous time audio, for example, continuous time video, had to be brought into this discrete domain so that the computer processed it. So understanding both is important. Understanding the relationship between the two is important. We're going to spend most of our time right here on the continuous side, just because most engineering processes, most natural and physical processes are going to be physical in nature, or are going to be continuous time in nature. But once you computerize it and once you digitize it, anytime you want to bring it to that world, we have to understand discrete time stuff pretty well as well. Okay. Any questions with this stuff so far? All right. So that's another characteristic or another classification. And now I'm going to give you the last of these classifications. So let me give you this pair, bounded and unbounded signals. And I think this will be easier if I show you, let's do it via an example. So let's have x of t right there. And let's have a signal that does this. So it kind of went up, went back down, and it kind of stabilized like that. They have another signal that does the following. And then it kind of keeps going. And as it's suggested here, it keeps growing and growing. So I think your intuition probably tells you which one is which. So this one on the top is going to be a bounded signal. The one on the bottom is going to be unbounded. Okay. So can someone tell me in words, knowing this, getting that visual concept, if someone asked you, well, can you put that into words? What does that mean? What does that mean to be bounded or not? How can you try to either verbalize it or express that? So let's get some thoughts from, yeah, I see Ryan with his hand up.
It has like a finite, like lower and like minimum value and maximum value, whereas the one where it's just like you can't give it a bound.
Right. So there's going to be the big thing is it can take a maximum value or a minimum value, right? Exactly right. So there's going to be a lot lower bound or and a higher bound. And so you can say, like for x of t, the minimum value it ever takes is 0. The maximum value is going to be, well, this one right here. For the other one, there's no maximum value. We know that it's going to keep going. Forever. And so we can't say, we can't put a bound on it. So that's exactly right. If you want to be as precise mathematically as possible, we're going to say that a signal is bounded. Signal is bounded. I'll say IFF, which means if and only if. If and only if. And a little mathematical terminology here. But are you familiar with the symbol that like at E, there exists? That's right. So this means there exists. Okay. So if there exists, let's say M, which M is going to be your bound. Okay, so if there exists, this is going to be a bound such that limit, or rather, let's even without the limit, we could say such that let's say x of t is going to be an absolute value less than m for all t.
For data, could you say like an unbounded or an unbounded signal wave is unstable?
So the terms of stable and unstable refer to systems and not to signals. So you're definitely on the right track. So a system that leads to signals that are unbounded is unstable. So indeed, we're going to be talking about stable and unstable systems a lot here, and it refers to this idea of, yeah, if something's unstable, it'll lead to stuff that's unbounded. Yeah, great. So definitely on the right track there. And this is just getting a little bit more precise. So with the signal, so basically there exists a bound. So it's going to be either a maximum or minimum value such that the absolute value of your signal is going to be less than that bound for all of time. Yeah, so there you go, bounded and unbounded. But yeah, in terms of applications, so examples, essentially, so to use John's suggestion, and I guess I'm skipping ahead a little bit, but like unstable systems, anything that's unstable in nature, so unstable systems lead to unbounded signals. And so you can imagine if this x of t right here is the velocity, let's say angular velocity or linear velocity of an object with respect to time, this is telling you that as time gets bigger and bigger, the object's just going out of control. It's just, you know, speeding the hell up, or, you know, just twisting this way and that, and just getting more and more intense as time goes on. So definitely you want to, with engineering applications, you want to keep everything nice and bounded. Or if it's an electrical signal and you've got something that keeps oscillating but keeps getting bigger and bigger, it's absolutely eventually going to blow up and ruin your system, and it's going to burn out all your parts. So unstable systems lead to unbounded signals. I'll say in engineering applications, let's say we want bounded signals for sure. Okay. Yeah, and again, kind of a bit of a preview. The problem with unstable systems is that even if you give it a nice and bounded input, they're going to produce an unbounded output. Great. All righty. So good work. So again, that's a lot of different types of signals. And as you can see, I think with each of them, I want you to be thinking back to the whole dual understanding. So you can look at all signals in this dual way of mathematical and physical, right, in terms of application. And so all of these, we broke them down mathematically, but they keep showing up in all these different realms of engineering application. All right. So let me shift gears here slightly and talk about some particularly useful signals that are going to show up again in all these different realms. So let's do this one, unit step signal. Let's say that's probably the most basic and maybe the most useful type of engineering, most useful type of signal that there is. So unit step signal, you probably remember it from back in circuits. So it looks like this. So I've got T here in my horizontal. Let's call it U of T here in my vertical. Essentially, it's going to be, take a value of 0 up until T equals 0. Then I'm actually going to leave this with a little open circle right there. And then here at time equals 0, it takes the value of 1. So that's the general shape right there for your unit step signal. So if you want to describe that mathematically, it's U of T is going to be equal to 1 for T greater or equal than 0, and 0 for T less than 0. Okay. So in terms of examples or applications, where would you think that you would see such a signal? So again, feel free to blurt out something if you're in person, or to type something if you're on chat. Yes, Ned.
Like a switch.
Switch, absolutely. So if you've got a switch, and specifically notice that it's going from 0 up to 1. So if it's a switch where you're powering something on, anything that's got an on switch, you're powering it on. So anything that you're powering on is going to be modeled by this unit step signal. Now, as you might guess, almost any type of engineering system, especially if you're thinking in the electrical computer realm, are going to be things that you are switching on at some point, right? Like you used to have no power at some point, and then you're flipping the power on. So indeed. Anything else aside from thinking of a switch that you might visualize that way as a step? So, I mean, this is like the main concept there of just switching something on. But if you've got so let's say a digital signal, and so it might be like a digital square pulse, where you're seeing things like this. You got like ones and zeros. Then really you've got a step right there. Steps coming back down. Then you've got another step like that. So that would also be examples of something that's using U of T in some way. So digital signal would be another example. Anytime you've got a sudden jolt or a sudden change from one level to another, that can be modeled as a step. All right, so let's practice a couple of things that we learned recently. Would you say that this signal, let's say, is U of T a causal signal? So look back at your definition right there, and you can tell me whether you think it's causal or not. And you can see Andrew. Oh, no, that's from before. Yes. So Tim says yes. See, Ryan is nodding. What do y'all think of the right of the class? Amy and you guys all agree. Yes. So indeed, there's a lot of yeses coming in via chat as well. So yeah, so you guys are absolutely right. It's going to be a causal signal. The reason being it takes a value of 0 prior to t equals 0. Great. So, someone joined in with audio there. Heard a little echo. Jorge, come on, man. It's all good. So is U of T, let's say, it's something basic, but let's say, is it bounded? And again, feel free to. Yes, I see John is saying yes. Let's see if there's people saying here on the chat. Yeah, so I think you guys can see, yeah, it's going to be bounded as well, because it's going to take a minimum value of 0, maximum value of 1. So there's a clear bound to it. It's going to be a continuous time. It's definitely not discrete time. It's going to be continuous time. What else did we look at? Is it periodic? Thomas Georgie says no, or as Jeff Edmonds says no. So yeah, but indeed the answer is that no, it's not. So it would have to repeat over and over. Whereas here you just have the one change. That change doesn't really repeat after that. So this is absolutely true. Great. All right. So let's keep doing a little bit of practice with this U of T to reinforce some of the concepts we've learned, not just in this class, but the one before and last week. So let me ask you to sketch. Can you sketch? Let's say a signal, let's call it G of T. And let's say G of T is 4 times U of T minus 1.5. So go ahead and sketch that. And if you're in the classroom and you got a pretty good idea, feel free to turn to a neighbor and show your drawing to a neighbor to compare. If you're at home, you can just let's see, you can check in with a friend if there's a friend you want to type to, and just describe briefly to your friend what it is that you drew. Or you can even hold it up to your friend if you want. Right. Okay, so hopefully y'all got something like this. So remember when you've got this T minus, it's a time shift. So it's going to kick in at 1.5 on the right side. And then it's going to have a height of 4 when it does kick in. So it's going to be a signal that does this. And prior to T equal 1.5, it's going to have a value of 0 like that. All right. So let's do another example. Let's sketch. Let's say G of T equals sine of T times U of T.
Dr. Estrada,
Yes, sir.
the bottom, the 1.5 up on the x-axis, is that a closed circle?
It's going to be open at the bottom and closed at the top. Yep, and it steps like that. Great. So think of this one. G of T is now sine of T times U of T. And just to help you out, I'm gonna show you what sine of T versus T looks like. So if I were to just plot sine of T versus T, so it's good old sine wave, so it's gonna be doing something like this. Something like this. Okay, so if I know sine of T looks like this, I'll plot G of T versus T on the right. Okay. And again, if you're here in class, feel free at any point to check in with your buddy and say, hey, is this shaping up this way? And if you're at home, I'd say type to a buddy and ask them, well, what are you doing? How is yours shaping up? All right, so I see at home Hunter has a nice plot there. Okay. How about anyone here in the classroom want to give me just a description of what you expect this to look like? Yes, Ryan.
It's off until 0 seconds for the sign first starts.
So up until there, it's going to be flat. And then what happens on the right?
It just starts like
Normal sine wave after that. So, yeah. Exactly right. So that's going to be, so exactly right. So what do you think, like if we were to put it into words, what did we do, like in terms of the technical terms that we learned? What did we do by taking this signal on the left and multiplying by U of t?
we made it causal.
We made it causal, exactly right. So another application of this U of t is, I'll say, a note right here. So multiplying by U of t. Say makes signals causal. Okay. All right, that's great. So let's do yet another example, getting comfortable here with this U of t, just because it is one of the absolute most useful signals. So let's see, can we express, example, let's express this signal, let's call it G of t again. Not piecewise, so we're not allowed to express it piecewise, but just in terms of unit steps. And so I'll show you a signal right here, G of t versus t. And all G of t is going to be is just going to be a 5-volt pulse. It's going to be 5 volts. It's going to kick in at time equals 3, and it's going to turn off at time equals 6. So you can think of that as a little electrical pulse. 5-volt pulse here got turned on. At time equals 6 got turned back off. So, I mean, I think some of you could say, well, we could express this as G of t as a piecewise thing and say, well, it's going to be 0 for time, let's say less than 3. It's going to be 5 for time between 3 and 6. Maybe you're including there. And then again, 0 for time greater than 6. And it's like, yeah, sure, you know, like that's fine, but it's a pretty like unelegant and an awkward way to do it if like you're describing every single interval. So can you express this in terms of unit step just in a single line? Can we, so this is true, but can we express this in a single line just by using unit steps. Okay, so try that on your own. If you have some suggestions, feel free to type them into the chat box. If otherwise you want to check with your friend and whether you're doing great or you're struggling a bit, feel free to turn to your friend here and ask them some suggestions. So I've got a suggestion coming in via the chat. So Andrew says, so let's see. So 5 bracket u of t minus 3 minus u of t minus 6. All right, so let me copy that down and see if that matches what Andrew said. So 5 bracket u of t minus 3 minus u of t minus 6. All right, Andrew, do you want to unmute yourself and tell us why you wrote it like that?
Easy way to think about the stepwise, the step function is, so before that minus 3, whatever is in there, it's 0, and after it, it's equal to 1. So at time equals, at time equals 0, u of t minus 3 is 0, and u of t minus 6 is 0. So it's 0 times 5. But then when it gets to time 3 and beyond, that u of t you can think of it as a switch turning on. So that'll be equal to 1. So that'll be 5 then. Or that'll be 1 minus, the other part will still be off. So it'll still be 5. But then once we get to 6 and beyond, both of them will be on. So 1 minus 1 is 0, and they cancel out.
Beautiful. Yeah, that's great reasoning. So again, if we just had this piece, so we just have that 5 u of t minus 3, then what we would have is something that's 0, 0, 0. It kicks on right here, and then it would stay on forever. So to represent this going back down, we need to subtract off 1, right? But so we want to create something that we would see subtracting off that would kick in at t equals 6. And so we do it that way. So this u of t minus 6 is going to kick on at that point right there. Great. So with that, let me give you a couple more examples and you can copy them down. And then I'll put you into little groups to wrap up those examples. So let's try these out, and these will hopefully get you, fairly comfortable with this type of reasoning and this type of how we handle these signals. So let's say we've got something like this. So here we've got a small pulse, a tall pulse, and then another small pulse. I'll call this one f of t versus t. So this is a height of 2. This is a height of 4. This right here is -7, -5. This is going to be 4, 6, 8, and 20. Okay. So can you express f of t? Let's try a tricky one here. So I'll give you a second one below it. Let's call this one x of t. And again, your goal is to express it in a single line. So let's say this is going to be a height of 6, and this is 6 e to the minus t over 3. So express as f of t, and express x of t, both in a single line. Okay, we got about 5 or 6 minutes. So start that on your own, and then I'll put you into a couple of breakout rooms here, so you can check in with some friends.
How wide is the, on the first example, on the left?
Can you move the paper over to the, I think, right a little bit?
Okay. So,
Thanks.
yep.
Thank you.
There we go. No problem. Sorry about that. All right, folks, I'm going to put you into breakout rooms. I think I've got students who are away with other students who are away for the most part. And otherwise, if you're here, you don't have to actually go into a breakout room. You can just talk to the people that are nearby. So if you're remote, go into the Zoom. If you're here, just talk to the people that are nearby. Austin Dalloway, did you get an invitation to a breakout room? Or are there two Austins?
No, I got
Okay, gotcha. I see an Austin Dalloway and an Austin. Oh, there's another Austin. Never mind.
Do you want me to join the break?
No, no, no. There you go. You don't have to. Like you can if you want, but I put you in a breakout room just with this class, so it doesn't matter. So yeah, so basically, if you're here in the classroom, you can. If you're here in the classroom, you can just talk to the people nearby. If you're remote, then you go to the breakout room.
Even though my son's carbon.
So two, and then in parentheses, you, basically, and then result bracket, and then I have a new bracket for U T minus 4 minus U T minus 6, and then I was bracketed, and then new bracket, U T minus 8 minus 8 minus 20.
Essentially, exactly right. I just tried.
Oh, okay, yeah. I guess they should. Yeah, I'm good. I don't know. I guess you start off just like being sick.
I'm saying,
And then,
it's just that it's like up and down if you add it to the down and outside. Yeah. Yeah. But that doesn't work. I think so just like with the sine wave, you just like treat the 60 and then you do a create fidelity to like it's turning on. So let's say you just multiply U T 60 and so thought that would be the same with the sine. And then to that I just added like 6 times U to the negative T. So it would switch the one.
Alrighty, folks. So I brought you all back from your breakout rooms. Let's check in together. So actually, now that you're back here, I think you're still seeing. Do I still have spotlighted the piece of paper? Yep. Okay, great. So you're seeing that before we dive in, I'm actually going to give you one more signal right there, and you may as well copy it. So y of t. And it's that sequence of pulses right there, sequence of pulses. It, as you can see, is a periodic signal. This one repeats every T1, and the duration of each pulse is T2. So T1 is the duration of the pattern. T2 is the duration of a pulse, and it repeats over and over again. So we're actually going to ask you to express y of t also in a single line using u of t's. So there we go. So hopefully you had a chance there with your group to come up with get the slide up there, to come up with a nice description for for at least for that first one, and maybe you were doing well with that second one. So I'm actually noticing the time, 10:42. So I'm going to leave you all in suspense. And you know what? These 3 examples. Let's change this from example to homework. I know you weren't expecting that, right? So there we go. So that's going to be our homework here to practice this stuff. Let's make this do Tuesday or Thursday.
Really? Thursday.
Thursday. All right. I heard some Thursday on the chat. Alec Leslie's shaking his head. He's like, no, Tuesday.
No, Thursday's fine.
All right. So yeah, so we'll make this homework due Thursday.
Wait, what were the heights of those pulses in the third signal?
Oh, great question. So let's make them of height A. Great. And this will actually, I think it'll take some subtlety. I mean, the first one is probably the easiest one. The second one probably will force you to look back at your notes. And yeah, and it's going to be a little bit more involved. And this third one, again, it might force you to get more comfortable with some of the mathematical notations. So definitely be ready for that. So I'll create an assignment via Canvas, and y'all can submit as usual. Take a photo of your work and submit that. Yeah. Otherwise, you can feel free to check in with your buddy, check in with me during office hours, and we'll figure it out. All right, folks. Thank you for your attention. Hope you have a good weekend. Enjoy being on campus or being at home.
Thank you.
Yep. See you soon. See ya. Take care.
Oh, yeah.
Do you want your goggles on? I don't think I need them.
I'm good. If you're not gonna use them, you can either pass them on to someone else or you can just toss them.